Our journey on the way to spirit from raw material now moves away from natural processes into scientific chemical manipulation to increase our alcohol by volume to the level of a spirit, as well as select components for inclusion and exclusion. Now, this lecture is a more technical dive into this manipulation, designed for those studying for their WSET Level 3 spirits, or those who watch the 200 level intro to distillation and want to dig deeper. We're going to assume that level of knowledge and get real nerdy. Hang on. All right, so we can break distillation into three parts. One being how we handle our fermented raw material inputs and get them to start vaporizing. Then secondly, what we do to those vapors before the final step of carving up those vapors for inclusion or exclusion. So our step one is vaporizing. Vaporizing is changing the state of material from solid or liquid into a gaseous vapor. Now, we use the word vapor instead of gas because our vapors include tiny liquid droplets, visible like the way you can see steam from a boiling pot, and it also contains invisible gases. This concept of visible and invisible is easy to understand in the way that we can see steam or clouds, but we can't see humidity, even when it's very high. We also know that the form water takes changes very easily between solid, liquid, vapor, and gas. A warm breath on a cold pane of glass instantly transforms gas to liquid. Pretty much all compounds can exist in solid, liquid, or gaseous stages depending on the amount of heat being applied to the molecules. And almost all compounds have different temperatures in which this happens. One of our primary molecules that we are after is ethanol, which turns into a gas at 78.3 C, while water does this at 100 degrees C, provided we are at sea level, or actually the atmospheric pressure at sea level. Getting those molecules to escape into a gas is affected by how hard we're squeezing them. Squeeze hard, more pressure, more energy is required. Less squeezing requires less energy. But more on squeezing and atmospheric pressure later. You should be familiar with the concepts of boiling points and their inverse volatility. But something with more volatility will have a lower boiling point, and higher boiling points relate to lower volatility. Ethanol is more volatile than water as it has that lower boiling point. Let's just stick with water, H2O, and ethanol, C2H5OH alone. One thing to know is that they love each other. Being polar molecules, which is a negative oxygen charge and partial positives on the hydrogen. Anyway, that allows for the formation of very strong intermolecular hydrogen bonds. And this love or attraction lets them exist together in pretty much any proportion. And while we won't really discuss the zeotropes here, just know that we do not have a way to separate them completely through boiling and vapor collection. Once we get to 96% ethanol, we can't get this liquid to give up more ethanol. The vapors that come off will have the same ABV as the liquid. But before that, back in, say, we have a 10% ethanol fermented liquid, we can get the vapors to have different concentrations than the liquid. Now we're going to follow the WSET methodology and call the individual components in our liquid fractions going forward. Our hypothetical pure water and pure ethanol mix is then comprised of two fractions. Now this fraction concept will make more sense later when we start to deal with thousands of them in a fermented liquid. So you might imagine that if you bring the temperature to 78.3 C, the ethanol would just turn into a gas and leave, but due to those bonds, it just won't. our 2-fraction ethanol water mix will have a boiling point of between 100 C and 78.3 C, depending on the concentration of each in the liquid. And if that ABV of the liquid changes, so changes the boiling point. This is a very important thing to understand. Now, why does it change? Well, the vapors coming off the boiling liquid are not pure ethanol, but do have a higher percentage of ethanol in them than the liquid. Expand this to 1,000 fractions, and the fractions with lower boiling points or higher volatility are going to be more concentrated in the vapors from the liquid when boiling at a lower temperature. As we increase the heat and the boiling point of the liquid gradually increases, our more volatile compounds have mostly already turned to vapor, and we change the concentration of the vapor to now include less volatile compounds as well. But we're only talking concentrations here. It's not a pure fraction separation or isolation. Now, before we move into the next step of dealing with these vapors, it should be somewhat intuitive to also assume that the application of our heat can manipulate these concentrations. If we take our liquid and boil the hell out of it, this violent boiling is going to contain a messier mix of fractions in it than if we did a slow, gentle simmer with gradual temperature increases. And just to circle back to our squeezing or ambient pressure changes, it's important to realize that the change in boiling points due to pressure is not perfectly relational, and that not all compounds' boiling points change due to pressure at exactly the same ratios. Now, we also may have compounds or fractions that change their flavor by being cooked or heated. If we can get those to go to vapor at lower temperatures, despite higher boiling points, we may be able to alter the way those present themselves later down the road. This is why you'll hear about gin makers using vacuum distillation for their delicate botanicals when redistilling it. But we'll dig deeper on that in later lectures. So now we've heated our liquid and we have vapors leaving the liquid. And just like inside the liquid, where these molecules are all jostling around before forming steam bubbles and escaping as tiny droplets and gases, the same jostling happens when they are in vapor form. The process of these tiny liquid droplets and gases banging together and changing their composition through these collisions introduces the concept of reflux. Now imagine that I'm one of these tiny liquid droplets that just escaped the heated liquid, and I'm mostly water, but I have a bunch of ethanol stuck to me as well with those hydrogen bonds. The temperature gets just right for me to float out of the liquid. But on the way up, I crash into somebody else, and that crash knocks off an ethanol molecule or two. Probably knocks off some water vapor too. Now I just became less volatile, or my ABV dropped, and I will sink to a warmer level where I can still float. But the air around me just increased its percentage of ethanol and became more volatile. The now higher percentage ethanol mixture will rise. This level where I can hang out is part of what we call a temperature gradient. This is the range of temperature from the liquid at the bottom, where the heat source is, and therefore hotter, all the way to where the vapor exits, which is the coolest part, making up a temperature gradient. Lower ABV gases and vapors will tend to congregate closer to the heat source, and higher ABV vapor will gather higher up, where it's cooler, but their lower boiling points allow this. If we have a small temperature gradient, we won't have as much separation compared to a large gradient. This temperature gradient can be created by a physically tall still, or by incorporating a device to cool the top of the still, creating a larger temperature gradient, as we'll see in later lectures. But back to our reflux for a moment. The more collisions or more reflux we have, the higher ABV we're going to be creating. This repeated reflux action and higher ABV outputs are defined as rectification. A higher rectified spirit is simply one where the ABV is higher coming off the still. A higher rectified spirit is cleaner, if you will, or is simply comprised of fewer of the lower ABV fractions. Now, cleaner may imply better, but it's better to think of it as being a lack of character. If we pull a spirit off at 96% ABV, it will taste and smell pretty much only of ethanol and those fractions that have very similar boiling points as ethanol. This very high rectified spirit are called neutral spirits, and that carries actually a legal definition in many countries and has a minimum ABV. If our goal is vodka, we want this high level of rectification. If we are after, say, an intense single malt, a big chewy bourbon, or intense mezcal, we need more fractions that have those desired congeners to be collected in our spirit. So, how do we control or manage this reflux? Not only does that temperature gradient impact reflux, we can encourage reflux by forcing those vapors to collide. In a pot still, we can change the shape of the still itself by narrowing it towards the top and creating bumps and voids where the vapors get bounced around, rising and trying to escape upwards. Now, like imagine a mountain stream of varying widths with boulders creating eddies. Whenever we push and shove the vapor or slow it down, we're going to encourage reflux. Now, we could also grab our vapors and force them back into a liquid to really encourage reflux. Now, we know these vapors increase in ABV with reflux, so each time we would do this, the liquid we crash it into has got to be a slightly lower boiling point or higher ABV, and also at a lower temperature. We can basically create another little distillation many times. And each time this happens, we're creating reflux and increasing ABV. As it gets cooler, it gets harder for water as a gas or as part of a tiny liquid droplet to keep rising. And that's similar with any fraction having a boiling point similar to water. Now, with a fermented base, we are dealing with thousands of components or thousands of fractions. Some may be desirable due to having a specific congener, and some may be undesirable or even poisonous. And then some have boiling points so high, so much higher than water, that they barely ever even turn to vapor at the temperatures that we're using. We're going to use the WSET concept of fraction grouping, as it makes this easier to get a handle on. Group 1 fractions are the most volatile ones. So let's take a common alcohol produced in fermentation, methanol, for example. Its boiling point is 64.7 C, or lower than ethanol. So with some reflux, it's going to be concentrated at the top or coolest part of the still. And methanol is a great solvent used in industry and pharmaceuticals, but it will kill you if you consume just a small amount. Group 1s included in your spirit will be easily detectable with a solventy character and often a physically painful, prickly sensation when you smell them. Our group 2 fractions are fractions with similar boiling points to our desired ethanol. Lucky for us, many desired congener fractions also live near ethanol in our second group. Then we have our group 3s, are some heavier alcohols and other molecules that can often provide a roughness or chewy, coarse texture. But some can also be plasticky or give a rotten, cheesy character. And then we have the group 4s, which are those that really don't vaporize much or contribute to the spirit being collected, but they do end up concentrating some fatty acids that we'll often use back at the fermentation stage. These group 4s provide the ingredients for our dunder, backset, or sour mash, for instance. So when we started this lecture, we mentioned not only were we wanting to concentrate ethanol, we were wanting a way to select and deselect fractions. This process of reflux and distillation is the ways this happens, as it divides the vapors into groups of fractions that we can now include or discard. Very importantly, The makeup of these groups varies according to all these considerations of reflux, temperature gradients, and raw material composition. Different still types and methods of operation make the groups more defined or less defined. And where one ends and another begins is a decision made by the still operator and the capabilities of the still itself. One man's group 1 starts to be another one's group 2, etc. Another important point to remember is that while we can concentrate groups, it's practically impossible to isolate a particular fraction. There's always a little bit of mingling or stuff that should be in group 1 that ends up in group 2 or group 3, for instance. Just looking at our ethanol, for instance, while it gets concentrated in those group 2s, some is still hanging out in the group 1s and the 3s, and some, though not very much, even gets trapped back in the group 4s. Now we'll examine the process of removing these groups when we talk about individual still types in those related lectures. Now you should already see that our group 1s that we remove are often called the heads, and the group 2s with our desired congener fractions and ethanol are our hearts, and the group 3s are often referred to as the tails. We'll also leave the process of turning these vapors back into liquids or condensing them, hence the term condenser, when we go into those still type lectures. Now, before wrapping this up, we kind of have to go back and revisit a WSET Level 2 spirits topic where it's stated that raw materials, their fermentation, and a spirit's aging and maturation are the flavor creation steps. Yes, for level 2, they are the primary ones, but now we're at level 3, and you'll see there's more to it. There is additional congener creation that can be encouraged during distillation. If we were to slow this whole process down and just give our fractions time to hang out together, some will react with others and form new fractions. For instance, our fatty acids and alcohols that may have wanted to hang out in their respective group 3 and group 1s can combine and form esters, new compounds that now slide into the group 2s. These esters, through this esterification process, can provide much desired floral and fruity congeners into our collected group 2s. And not only can esterification happen while reflux is going on, a little direct heat, which is often less precise and creates hot spots in the liquid, can promote esterification more than an internal steam coil heating method. Now, these same hot spots can also facilitate Maillard reactions. These are reactions between sugars and amino acids due to heat. It's what changes the flavors of a grilled protein compared to, say, sous vide cooking. In brief, sugars and amino acids form a new unstable compound that then breaks down and recombines, eventually creating those complex and often desired congeners we associate with direct heat cooking. The composition of our fermented base, its amino acid content, whether we have dead yeast cells in there, and other components combined with the heating methods give us the opportunity to encourage or discourage Maillard reactions. Esterification and Maillard reaction science and their resulting myriad of compounds is fascinating and warrants its own lecture. We do dive deep into Maillard reactions over in our cognac lectures, and esterification is a vital topic we explore more over in our cane spirits lecture. And lastly, we have one more topic to discuss regarding selection and deselection of congeners that doesn't fit into reflux and temperature gradients. Many different yeasts often produce varying amounts of sulfur compounds during fermentation. Unluckily, these are very noticeable to our olfactories, and many of these will want to congregate in our group 2s. Some spirit styles, notably in Asia, embrace the sulfur, funky, rotting vegetable, burnt rubber, meaty character that is associated with these sulfur compounds. Other styles don't. But you can't easily cut these out through fraction selection. But when hydrogen sulfide and sulfur dioxide vaporize and start moving up our still, if they come into contact with copper, they will react with it and turn into copper sulfide, and then just stick there, becoming a solid and no longer being a gas that can escape the still. If we want to control sulfur, we can put plates of copper somewhere in the process, or just make the whole still out of copper. The downside is that this reaction requires those sulfur compounds to touch the copper. Once the copper sulfide is all over your copper, it won't do its job anymore. So you have to clean that black stuff off so copper is again exposed. So hopefully we were able to explain distillation fundamental concepts, and you now have a handle on what happens during any distillation, from reflux, rectification, grouping of fractions, and what tools and applications of tools during distillation, what they contribute to what you taste in the bottle. Understanding these fundamentals is vital to understanding and demystifying how our widely different still types all apply these concepts to produce what they do. See you next time.